Bayesian classifiers. So as you can see from this title, this classification method is based on the Bayes theorem. So we have to first take a look at the Bayes theorem, which is shown in this slide. And before knowing about it, we should know the joint probability. The joint probability is simply the probability that event X and event Y happens together, or these two can be a sort of random variables. So the joint probability can be written like so. This one is a simple expression. Actually, this expression means that x in the random variable case, x equals to x and y equals to y. So these are specific numbers, specific values, and the conditional probability y given x is the probability that y happens given that event x already happened, and that is given by this formula, which is the joint probability of the x and y over the marginal probability of x. And likewise this one, the joint probability of x given y, which means that I want to know the probability that x happens given that y already happened. Then it is because we are considering these two events. So the numerator part is the same as before, and just the joint probability of x and y, and the over the denominator part becomes the marginal probability of y. So if we use these two formulas, these two equations, we can easily derive this equation, this equality. The conditional probability of y given x equals to, it becomes this one over the marginal probability of x, because this one came from this equality. So we simply replace this joint probability with the multiplication of these two terms, right? Multiplication of these terms comes here, and this marginal probability comes here. So we can express this conditional probability in this expression. Okay, and here actually the Bayes theorem is, let me give you a little more explanation about the Bayes theorem. Bayes theorem is a way of finding the probability of cause given that a consequence has been observed. Okay, I think this one is the simplest way to express about the Bayes theorem. It's the way of finding the probability of cause. So it's about cause and consequence. The way of finding the probability of the cause given that a consequence has been observed. So we want to know the probability of cause y given that a consequence has been observed. Okay, then this probability is the probability of consequence, and this one is the probability of the cause itself, and then this one is the conditional probability of consequence given that a cause is given. And in fact this part is just to express about explaining about actually this one is the same formula for the Bayes theorem. And let's take a look at this figure. This omega is the whole sample space. The sample space is a space of the events, and then it is divided into disjoint subspaces from B1 to Bn, and there is a intersection, event of the intersection, which is A, and we want to know the probability. Actually, we observed a consequence A, and we want to know why this one is happened. Is that because of B sub I? We want to know that probability. And that is given by the Bayes theorem. So this numerator part, you can easily get this numerator part from the scheme of these two equations. But this numerator part is actually the weighted sum of the probability of A. Actually, the conditional probability A. So this one indicates that the probability of A given that Bj. So for example, what is the probability that event A happens if this sub Bn already happened? That is expressed by this one, Bn. And then we multiply the solely probability of Bn. Okay, and we add all those things. Actually, this one is Pi for the whole sample space, and that this one is called law of total probability. To find this marginal probability, we should employ this law of total probability. Okay, so you can see that this one is kind of weight, and this whole thing, this whole numerator, I'm sorry, the denominator is the weighted sum of conditional probability. Okay, then let's take a look at an example here to better understand about the Bayes theorem. There are 1,000 coins in a jar, and among those, 999 coins are normal, which means that these coins have both head and tail, but one coin has only heads. One coin has two heads. And so in this jar, there are 1,000 coins here, but we cannot see inside it. And we know that there is only one coin has two heads. One coin has two heads. And we randomly picked up a coin from this jar, but we didn't see yet this coin, this picked up coin is a normal coin or abnormal coin. We just tossed it. 10 times, and all outcomes are heads. Okay, we tossed it 10 times, and 10 heads have been obtained. Then the question is, what is the probability you picked up the coin having two heads? So here in this example, the consequence is 10 times of heads. Okay, that is already happened. That was already happened. Then the cause, then what is the cause? Is that because I picked up a normal coin, or is that because I picked up an abnormal coin having two heads? So to solve this problem, we have to define three events. The first one, let us say that let y1 be the event of picked up the coin, picked up the coin having two heads. And the event y2 is picked up a coin having head and tail, normal coin. And event x is we observed heads 10 times. Then the question is, what is the probability you picked up? What is the cause? What is the probability of the cause? What is the probability you picked up picked up the coin having two heads, given that 10 heads have been observed. Okay, then by the Bayes theorem, this can be easily solved. So the numerator part becomes probability of x given y1 times probability of y1 over probability of x. Okay, then what is this probability? The probability you pick up the coin having two heads is 1 over 10,000, is that right? Times, what is this probability? You picked up the coin having two heads, that is given. And if we toss this coin 10 times, what is the probability that we observe 10 times of head? Is 1, right? That is numerator part. Then what is this probability? What is just a solely probability that we observe 10 heads? Actually, this case should be split into two possible cases. Okay, so we have to consider two possible cases, where the first one is the case where we have the coin having two heads, which is y1. And the other case is we picked up the coin having head and tail, which is normal coin, y2. We have to think about these two cases, and this conditional probability is multiplied to this one times probability x given y2. Okay, so actually we already found this value. What is that? Is this one is 1 over 10,000, right? Because this one is 1, this one is 1 over 10,000. And what about this one? What is this probability? Estimated probability, in fact, is 999 over 10,000, right? In times, what is this probability? If we pick up a normal coin, then what's the probability that we will observe heads 10 times? That is 1 over 2 to the 10th. Okay? We add these two. So this part, this denominator part, is the case of what? Total probability, law of total probability. Then actually this value is very close to 0.5. Okay, so we just review the Bayes theorem. The reason that intuitively, the reason that this value is very close to 0.5 is that in the case where we picked up a normal coin, it's very hard. It's very hard to see 10 times of heads, right? That is almost, that is this value. That is almost 1 over, as I know, this 2 to the 10th is 10,024. So that is very close. That is very small probability. And the other case, on the other hand, if we it is very difficult. It is very hard to pick up the coins having two heads. That probability is 1 over 10,000. But once we have that coin having the observing heads 10 times, that is not difficult. That is the probability of that is 1. So the former case, in the former case, it's very easy to pick up normal coin, but it is very difficult to observe heads 10 times. But in the latter case, it is very hard. It is very difficult to pick up the coin having two heads, but it's very easy. Once we picked up that coin, then it's very easy to observe heads 10 times. So that's why the probability is very close to 0.5. It's as I know, it's a little bit greater than this value. So we can calculate this conditional probability using Bayes' theorem. So from this example, I hope you please understand this meaning. The Bayes' theorem is way of finding the probability of cause given that a consequence has been observed. Okay, so that's Bayes' theorem. And moving to the classification context, actually we can use this concept for classification task. Each independent variable xi and the class variable y as random variables. Then assume that we have observed data points, which means that x1 is some specific value 10 and 12 and xp is 0.5, something like this. And the goal is, in the classification task, our goal is to predict the class of this new observation, right? Then specifically what we want to do is we want to find the value of y, the class label that maximizes this conditional probability. In fact, this one is also called posterior probability. Posterior probability. This conditional actually, in fact, coming back to this slide, this one is a prior probability, and this one is called posterior probability, which means that for now I know, or I assume, the probability of this one as something. Then after observing, after some event happened, what is the probability? How this probability of y changes? We want to know that. That's why that name is called the posterior probability. Anyways, given these values, if we can find the probability of y, for example, in the case of two classes, positive class and negative class, if we can find the probability y equals to positive, given that x1 is 10, x2 is 12, xp is 0.5, and if we can find the probability that y becomes negative, I'm sorry about this happening, but I don't know why this thing is happening. So if we can estimate, if we know the value of this one, the probability y becomes negative, given that x1 is 10, x2 is 12, and xp is 0.5. If we can find these two probabilities by comparing these two, we can assign a class label which is corresponding to the maximum value. If this one is greater than this one, then we can assign the positive class label to these new data points. Or on the other hand, if this one is greater than this one, then we assign the negative class label to this new observation. Then the question is, can we estimate this posterior probability, this conditional probability, directly from our training set? Actually, the answer is yeah, the answer can be yes and no, both, but I would say no. It's very difficult to directly estimate this one, even specifically for the large data set, having many number of independent variables is almost impossible. So the answer is actually no. And we will learn about how to estimate this one from the data set from the subsequent lecture slide. So in classification task, the classification approach is compute the posterior probability, this conditional probability, for all values of y, for all class values of y, using Bayes' theorem, Okay, we can employ Bayes' theorem to compute this one. That is defined by this thing, right? The prior probability of y and conditional probability of this one, conditional probability of these all these joint events, and then probability of the joint events. X is joint event, and then choose the value of y that maximizes this probability, as I explained it to you just before. Then, because this denominator part is same for the case for the all values of y, so we can actually ignore this denominator part. So that is equivalent to choosing the value of y, choosing the class value of y that maximizes this numerator part only. Okay, because the denominator part is the same for all values of y. Okay, then still it's very difficult to estimate. Actually, this one becomes simple to estimate this probability, but because of these whole joint event or joint probability, actually this one is conditional joint probability of x1 through xp, so it's very difficult to directly estimate from our training set. So what we have to do is we first incorporate the chain rule. So again, coming back to the previous slide, we want to choose the class value of y that maximizes this quantity, this probability, okay, that comes here. Then by the definition of the joint probability, please remember, I'm sorry, by the definition of conditional probability, please remember this. This conditional probability, the first term, is equivalent to this one, the probability of whole joint distribution, the probability of this whole joint event. This one over this one, okay? This part is equal to this one over this one, right? By the definition of conditional probability. And on both sides, on both numerator and denominator part, we multiply the same probability here. Then this equality holds, right? And this P of y, it comes here, okay? Then we can see that this equality holds, right? Then this first term becomes this one by the definition of the conditional probability, right? Is that right? Probability of x1 given x2 through y. And how about this one? This one becomes this conditional probability. Okay, the given y, the probability of these whole joint events. And this one just comes again. Then what we're gonna do is we do the same thing for this one. So this one can be rewritten as probability of x2 probability of x2 x3 dot 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 xp and what, y over p of y, right? And we multiply the same probability on both sides, here and there. Okay, what is that? That is probability x3, okay, x4, xp, and y. The joint probability of x3 from x3, x4, dot, 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 xp, and y. Then this one, this part becomes this thing. Can you see that? Okay. This term becomes this conditional probability, and this part becomes this conditional probability. Okay. Py, it comes as is. So we do this thing again for this term. Okay. If you repeat this procedure, then the first expression, this mathematical expression, equals to, that is equivalent to this one. Okay, the thing is that in this part we have only one random variable. Okay, can you see that? Yes, so we can see that all of these equalities are satisfied. They are holding. Okay, but the thing is that still, because of these joint events, this no, not this one is easy. Because of these ones, actually still estimating these conditional probabilities difficult from the actually estimating those conditional probabilities from the training set is still difficult. It's not easy yet. So after incorporating this the chain rule, we have to adopt another concept to make this problem easier. We have to adopt another concept, which is conditional independence. And let me read this sentence. Let x, y, and z denote three sets. Please notice that this is a set of random variables. So three sets of random variables. So for example, x can be a set. X is a set. It can have only one element, or it can have multiple elements. Just like this. It's the same for y and z. So they are the sets of random variables. And the variables in x are said to be conditionally independent of y given z if the following condition holds. If this equality is satisfied, then we say that x is independent of y given z. What does this equality mean? Y does not affect at all to this x. They are independent in the situation where this random variable is given. So here's an example. The joint probability of traffic, lane, and umbrella can be rewritten by this thing, right? Can you see that? Because the second term is the probability of traffic and lane over probability of lane, and this can be cancelled out. These two we can cancel these two, and then this conditional probability becomes probability of umbrella, lane, and traffic over probability lane and traffic, right? So these two can be cancelled, then this one remains. So we can see that this equality holds, right? So this joint probability can be rewritten by this expression. And the thing is that, let's take a look at this part and this part. The conditional probability of umbrella given rain and traffic can be equal to the probability umbrella given rain. So it's raining out there, and if it rains, usually we have a traffic jam on the road. So rain can be a cause of the traffic, and because outside is raining, we should take umbrella, right? But between these two events, taking an umbrella and having a traffic jam, they are independent. They do not affect at all each other. So this probability, the probability that I'm gonna bring an umbrella, given that outside is raining and there's a traffic jam, is equal to that I'm take the probability that I'm taking an umbrella, given that the outside is raining. Okay, so we say that this umbrella and traffic, they are independent given raining. Okay, so this is a conditional independence. So we additionally incorporate this conditional independence assumption in our classification task. So here I made this sentence: our life becomes much easier with this conditional independence assumption. So assume that the predictor variables xi's, they are independent when a class value is given. So actually this part, the first line and second line came from this slide. This one and this one. We saw that this one is equal to this thing. Okay, so these first two lines show that, and I said that, I talked to you that estimating this probability from training set is difficult. Estimating this probability from the training set is difficult. But if we assume the conditional independence among those x variables, then this conditional probability becomes this one. By what? By conditional independence assumption. Okay, then this conditional probability becomes equal to this one, because all those x variables, they are independent given y, given the situation y y value is given. Then we have much simpler form for the posterior probability. Okay, please do not forget that actually this one is the probability of y given x1 through xp. We want to find this posterior probability, and that becomes this one. Then why estimating this one is easier than this one? Because we don't have to think about, when we compute this one, we don't have to think about x2, x3 to xp. We just take a look at x1 and y. Only two columns from training set. When estimating this one, we only take a look at just two columns, x2 column and y column. But if we have to estimate this probability, we have to take a look at x2, x3, x4, all x variables except for x1, and y column as well. Okay, so estimating this one is much easier than estimating this probability. If we will take a look at an example, then you can understand what I'm talking about for now. So we can estimate, we now can estimate this conditional probability for all xi and a specific value of y. If we have to classify a new data point, then we compute this probability. Actually, this one is equivalent to this one. This part is this part. And the multiplication of conditional probability is expressed by the product of conditional probability. And we assign to the class which is corresponding to the maximum value of this one. So we compute this posterior probability for every possible value of y. If if the problem is two-class classification problem, such as, for example, positive and negative, we compute this probability for positive and negative. If there are three classes, class A, B, and C, then we compute the posterior probability for all those three classes. Okay, so here is an example. Actually, the first three columns, they are x variables. This one is x1, x2, and x3. Okay, the first one is, do you own a home? And the answer is yes or no. And the second column indicates that whether a person is single or married or divorced, sadly. And and the third column is annual income. So these two are discrete variable, and this one is a continuous variable, and this one is class variable, which is y. Okay, so is this guy defaulted borrower, meaning that here the defaulted borrower means that if the answer is yes, this guy, this fifth person, borrowed some money from a bank, but he didn't pay back on time. That is defaulted borrower. So if the answer is no, then this guy borrowed some money and he paid back on time. This guy did not pay back on time. Okay, so this one is y. So this problem is kind of real problem that can appear in real bank. So in bank, they actually the business model in bank is they actually they how to say the give some money to people and then get some interest, and that is their profit. And then or people, they deposit some money to the bank and then they give people some interest, but that interest is much smaller than the interest that they got from people by lending some money, right? So they, whenever they lend some money to person, so a person, walks in a bank and this guy asks to borrow some money from that bank, and then the bank should make a decision whether or not they lend the money to this guy. Then they want to predict whether or not this guy will pay back on time or delay. They want to know that, right? So this is a real situation. This can be a real situation, and in practice, in real practice, the bank in the bank, the data analytics people, they do this kind of job. So this one is a class variable. We have three independent variables. So obviously, in real problem, in real situation, we have to consider much more independent variables and a lot more, observations. Anyways, this one is a kind of a toy example with a very small size, but it's very enough. I think this example is enough to understand the Bayesian classification. And okay, I forgot the name of this classification. That this one is called naive-Bayes classification or naive-Bayes classifier. The reason that we add here naive is because we do this conditional independence assumption. But in real world, actually, it's possible that there's some dependencies among the x variables, but we just simply assume that they are independent. Okay, so that's why this classification method called naive-Bayes classification. And coming back to this example, so what we want to do from this is we want to predict the class of new observation, and actually that is in this slide. So from this table, what we have to what we have to do to train a classification model is that we have to estimate all of these these conditional probabilities and this prior probability. So estimating the prior probability is given here. What is the probability y becomes no, y equals no, based on our data set? There are 10 people, 10 observation, and there are 7 no's. 1, 2, 3, 4, 5, 6, 7. So we estimate like this. We estimate this prior probability by just taking a look at the portion of observations having no value on y column. And then likewise, the probability y becomes yes is 3 over 10. Okay, these are the priors, okay, prior probabilities. So the way of estimating the probability for the conditional probability for discrete attributes is this one, is given by this one. The probability, conditional probability of xi given y equals j is estimated by this one, where this n of yj is what? Is the number of observations having this y value, and this one is the number of observations having the variable xi that belongs to class. So it means that this one is the okay, that belongs to class J, right? So for example, the probability marital status, which is x2, the probability x2 is married given y is no. To estimate this probability, we just consider the rows having the value no on y column. This one and this one, 7 rows. Among those 7 rows, how many rows have merit value on x2? There are 1, 2, 3, 4, right? So this conditional probability that marital status becomes married given that defaulted borrower is no is 4 over 7. Okay. Then for another example is then what is the another example is what is the x2 is single given y is no. Among those 7 rows, count the number of rows having single value on the value of single on x2 is 1, 2, 2, right? So this probability becomes 2 over 7. Okay, so another example, what is the probability homeowner x1 is yes, given that defaulted borrower yes? In this case, we just simply taking a look at this row, and this row, and then see how many rows are having the value of yes on homeowner column. There's no, there's no yes rows, right? So the probability becomes 0 over 3, which is 0. Okay, this is the way of estimating the conditional probability, all possible conditional probabilities from our training set. Then we can do that. We can estimate this conditional probability for the discrete variable, but what about this continuous variable, the annual income? So for the continuous variable, what we do is first one is discretize the range into bins. One ordinal attribute per bin, but this one can violate independence assumption. So there's a little risk for this thing. But what does this mean is, because in our example, the annual income ranges from 60K to 220K. So from 60K to 220K, we divide it into several bins. The number of bins are up to you. The number of bins is up to you. You can, for example, you can divide into 4 equal spaces, or such as 100, 140, and I don't know. It should be more than 4, just like this, and assign a nominal value, just such as 1. So we make this continuous variable discrete by discretizing this continuous space. So 1, 2, 3, we can assign some ordinal type value to this random variable. Or even much simpler, we can just split into two bins. So this whole thing from 60 to 220 is divided into 2 things, and the median is, what is that? Is 280, 140, then 60. I don't know. What is that? Anyways, we can divide it into 2 splits and assign a nominal type, ordinal type value 1 and 2. We can discretize even simpler. So this method is much even much simpler than this one. But the thing is that we take the risk of losing the information that continuous values have. Okay, more, this case is more loss of information. This case is less loss of information. As we discretize into less bins, as we discretize a continuous variable into less bins, then we lose more information naturally, obviously, okay? Or we can employ a continuous distribution, continuous distribution such as normal distribution. So we can assume that the specific variable follows normal distribution and use that column to estimate parameters of the distribution. For example, in the case of normal distribution, we have to estimate mu and sigma square, right? Mean and variance. And once the probability distribution is known, we can use it to estimate the conditional probability, this thing. So for example, here, in the case of annual income example, we use the probability density function, right? We can use, if we assume that this column follows normal distribution, then we can employ this normal distribution, the probability density function, right? Once we know the variance and mu. But the thing is that this one is conditional probability density function. So to estimate this thing, we have to consider 2 cases where the first one is y equals to no. The second case is y equals to yes. Okay, so this case so the first case y equals to no, then we should consider only these 7 laws. So using these 7 values, we estimate the average of these 7 values, which is the 110, and then we calculate sample variance based on these 7 values. Okay, then now we can compute the probability. Actually, this is not a probability. Precisely speaking, this is a probability density function value, because this is a continuous random variable. Okay, but let's just simply say that this is a probability. Then what is the probability income x3 equals to 120 given that y is null. Is based on the estimated parameters we can employ. We can use the, the probability density function of normal distribution, right? By replacing this part as a variance. Actually, this one is, it seems that this one is a standard deviation and variance and mean, right? And then just put this 120 here, then we can calculate the probability density function value. So we can do the same thing for the case of defaulted borrower equal yes. And we can compute the income equals to 120, right? To compute this one, we first have to estimate mean of these three observations and the sample variance of these three observations. Okay, then we can compute the conditional probability for continuous variable as well. To do what? To do naive-Bayes classification. So this is the what I have explained so far is the process of training naive-Bayes classifier. Okay. Then the purpose of classification is we want to predict the class label of a new object, and let us say that this one is a new object. This x1, this record. So there's a person is coming to the bank, and this guy has no home. This guy doesn't have his own home, and but this guy is married, but this guy's income is 120K, but this guy's income is better than me. And okay, it's saying that we don't have home, we don't have house, and this guy's married, and the decision maker at a bank should make a decision whether or not the bank gives some money to this guy or not, and then the bank must be able to predict whether or not this guy is going to be a defaulted borrower or not. So to predict the class of this guy, this new guy, what we do is we compute the probability y becomes null given x1 is null, x2 is married, x3 is 120. And we also have to find the probability y equals to yes given x1 is null, x2 is married, x3 is 120. How do we find this probability? That is the multiplication of probability y equals null and product of what? Xi given y equals null. That is, this part is given here. Okay, the product of conditional probability in the case of y equals to null, the defaulted borrower is null. So that conditional probability is this one. x1 is null, x2 is married, x3 is 120, given y is null, y is null, y is null, right? This conditional probability, what is that? The homeowner, okay, this is not refund, this is homeowner. Okay, homeowner is null given y is null. That is 4 over 7, this thing. And x2 is married, marital status is married, given y is null, is this probability. Okay, so this one, 4 over 7. And the conditional probability density function value of x3 equals to 120 is Is it computed? Yes, is this that one computed in this slide? So this one, so that becomes this thing. We multiply this value. Actually, to this value, we multiply this value. But that is 4/7, and we compute this probability here. So this probability is probability y becomes yes, and the product of conditional probability x I given y is yes. They are given here. Okay, y is yes given, or given condition is y is yes and homeowner is no, and marital status is married and annual income is 120K, then bring those conditional probability from this table, then the first probability is homeowner is no, given y is yes, the probability is 1, and this probability is marital status married, given deported borrower yes is 0, right? So 0 comes here. Then actually the product of this probability becomes 0 because of this one. Okay, then now what? This posterior probability is 0, and this posterior probability is greater than 0. I don't know what the value is. That value is 0.0024 times 4/7. Okay, that value is greater than 0. So we assign this new data points to class no. Okay, so the bank will predict that as that this guy will pay back on time. So the decision is okay, give this guy money. Okay, so we predict as no. So do you understand how naive Bayes works? So do you understand why estimating joint probabilities is difficult? I think you understand why. We have to take a look at all those columns at the same time, but estimating this conditional probability is much easier because we just take a look at these two columns from the training set. Okay, so once we have a training set just like this, the training procedure of naive Bayes classifier is to estimate all those possible conditional probabilities, and if there are some the continuous variables, then we have to, on the assumption that those follow normal distribution, we have to estimate the 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 probability parameters such as mean and variances. Okay, or you can even discretize those continuous variables. You can split into multiple bins, or you can split into 2 bins. Okay, then actually here is a problem, because we observed a problem, because this posterior probability, the way of estimating this posterior probability is in fact multiplication of many probabilities, right? So numerically the value is pretty small, very small, the value of this one. That the reason is that because we do not consider the denominator part in Bayes theorem formula. But anyways, this posterior probability, in fact, as you can see from this one and this slide, these examples, is a multiplication of many probabilities. But in this case, in among those many probabilities, even though only one probability is 0, just like this whole thing, this whole multiplication of many probabilities becomes 0, right? There's this kind of risk. So to avoid this risk, the first sentence says that if one of the conditional probability is 0, then the entire expression becomes 0. So to avoid from this, what we do is these two things. The first one is called Laplace correction, and second one is called M-estimate correction. Okay, we make some correction, little correction, when we estimate a conditional probability. Actually, this one was the original way of estimating this conditional probability for discrete column, discrete random variable. We consider the laws having yj value on the y column, y class variable. Among those laws, we count the number of laws having xi value. Okay, xi value on that some specific value. But the thing is that if this one is 0, the entire conditional probability becomes 0. Even one conditional probability is 0, then the entire expression becomes 0. So instead of using this one, we don't use this one in practice because of this risk. So we add the number of classes, so J is number of classes, to denominator, and we add 1 to numerator. So even though this one is 0, the numerator becomes still 1, so it's not 0, even though this value is pretty small. Okay, so the reason is that the intuition behind this correction is that, okay, among j laws, j observations, at least it's possible to have at least one observation having, this specific x value. So it's a little correction. So usually, because we usually use a training set with a big enough size, so even though we use this kind of correction, there's no big distortion or big, bias for estimating this. There's no big bias, there's no big distortion for this conditional probability, so we can do that. And another way to make a correction is called M-estimate correction. Is actually the intuition is the same, actually the scheme is same, but we add this MP to numerator, where the M is sample size and P is the prior probability. The prior probability of this one. So the P equals to P, Y equals to J. And the denominator, we add the number of samples. So for example, if we have 100 observations in our training sample, then we add 100 here, and we add, for example, if there are 30 laws in there, then we add 30 to the numerator part. So actually this is another way for making a correction, but usually what people do is this Laplace correction. Okay, actually in our software is also implemented by this scheme, this Laplace correction scheme. Okay, and here is another example, but there are several slides. I want to stop at this moment, and then we will keep going on from the next slide, from the next session. And thank you for your attention. I will see you again.